Okay, so this is section 3.2, part 3. All right. The last page talks about alternate notation for derivatives. So given that y equals f of x, so y equals a function, the derivative of y with respect to x can be written many ways. The first one is f prime of x, or we can just say y prime, because remember f of x is y, right? We can also say dy dx, or df dx. This means the derivative with respect to x, the derivative of the function with respect to x. Or capital D sub x f of x. That means the derivative with respect to x of the function. Excuse me. So f prime of x is useful when referring to the derivative of a function or interpreting the slope of the tangent line to f of x at x. So dy dx is useful when interpreting the derivative as an instantaneous rate of change. So we're going to see this notation a lot when we do instantaneous rate of change, because if we write it up as dy dx, we're able to cancel some stuff out, and you're going to see we're going to have like double derivatives, etc., or even with integration. So we can write this up as dy dx, or the limit as the change of x approaches 0. So we have the change in y over the change in x. And if you remember, the change in y is actually the formula for slope, right? So remember, slope is your instantaneous rate of change, and the derivative gives you the slope at a point. So remember from the previous example, we're just going to write it with alternate notation. The function at x equals the square root of x minus 1 when x equals 5, right? So the function itself is f of x equals the square root of x minus 1. The point when x is 5 in the function, the result is 2. So therefore, x is 5 and y is 2. And that's what this says over here, right there. Okay? Versus y equals the square root of x minus 1. Remember, f of x is y, right? And then we go on to say the derivative of the function, or f prime at x, equals 1 over 2 square root of x minus 1. So that's your slope. So your slope when x equals 5, or f prime at 5, equals 1/4. So we're talking about instantaneous rate of change. We can also say the derivative is dy over dx equals 1 over 2 square root of x minus 1. Another way that you can see slope when x equals 5 is dy dx such that x equals 5 equals 1/4. So I just want to point out that that line reads as evaluated at or such that. So evaluated, and I spelled that all kinds of wrong, but we're this derivative is evaluated when x equals 5. So if you plug that in the slope formula, you're going to get the result of 1/4. So notice how we have this little subscript that says x equals 5. That's telling you what to plug in. You will see this notation again. All right, let's do example number 6 and call it a day. So example number 6 says, write the derivative with alternate notation. For s at t equals negative 16t squared plus 80t plus 100, we found the instantaneous velocity at t equals 1 second. Write with alternative notation. So the derivative of s at t equals negative 32t plus 80. So alternate notation, we could say dy with respect to t, so it's going to be dy over dt equals negative 32t plus 80. And then another notation we could do is dy dt evaluated when t equals 1. Do you notice how it says when t equals 1? It equals 48. Okay? So that's just alternate notation. For part B, we have to rewrite this. So the function b evaluated at 1 equals 2,000, and the derivative or the slope at that function at 1 equals 1,200. So if we're going to write up the slope, I'm going to write it up as b, the derivative of b with respect to t, because see that axis is t, evaluated when t equals 1 is 1,200. Okay? And for part C, if we rewrite the derivative, we rewrite this as the derivative of t with respect to, now this time away it's h because it says h here, evaluated when h equals 2,000 equals negative 0.005. Okay? So that's what they want you to do with that last page. And by the way, congrats, because we are done with this section. Okay, so please upload your notes to Canvas, like all 3 parts. And that's it. Have a good night.